We're going to take a look at another method of approximating the area underneath the curve without using antiderivatives. So this is a little recap of what we've done so far when we've been approximating. So we've approximated with rectangles, and so when we do that, we have the top of each of the rectangles defined by a constant. So when we drew a rectangle, so let's say this is our region, we would define a horizontal line to be the top of each of these. Then we tried to improve that and said, well, horizontal lines kind of stink, especially when things are going up and down, right? But approximating with trapezoids, at the top of each of the trapezoid defined by a line with any slope. So here we could define, say, the trapezoid now with a slanted line, right? So we were able to draw some type of horizontal line to connect the endpoints. But if we now think about how do I improve things, so I have a horizontal line, go to any type of slanted line. This is a constant. This is going to be something where there's an x present, say y equals mx plus b. To improve that, we're going to use a quadratic, right? So if we just keep increasing the power of x's, that seems to allow more curves to appear in our function. So we can use a quadratic passing through the endpoints and the midpoint. Because to define a quadratic properly, you need to have three defined points to define any quadratic. So let's say this is our region that we have. We would define a quadratic to define on this by saying on this first region, I have these two endpoints, and then I would pick the midpoint of this and go up to this. Then I would find a quadratic that passes through these 3 points. So it would be, say, something like this. And then on the next region, I again use the midpoint here, and then I define a quadratic that passes through these points. So notice that's really, really nice when you compare that to what you would have gotten from the previous two methods. So using a quadratic will help us because when we're looking, especially when we're looking at curvy things, that's going to be nice. Now, when we start to define this a little bit, we use that x sub n subscript last time. What this would look like in this case is that this would be our x sub 0, this would be x sub 1, this would be x sub 2, this would be x sub 3, and this would be x sub 4. So in the previous ones, the n really helped us define how many regions we were looking at. Here, the n is really going to say how many distinct points are we using in this process. So here we have 5 of these points, x sub 0, x1, x2, x3, x4. But n in this case, this would say n is equal to 4. Because our last endpoint here, this wherever we're ending at b, that subscript is our n value. So that will help us when we use this formula. So this process of using the quadratic as opposed to linear or constant, this is called Simpson's rule or Simpson's method. So the formula for this is going to be b minus a divided by 3n, and then we have the sum. So we've seen the sum so far with rectangles, we saw it with trapezoids. Trapezoids, it looked a little bit different, right? Because we had 2's appear as coefficients some places. Here, we start out with just 1 as the coefficient as this first endpoint, but then this middle one is going to have a 4 appear. Then we're going to have 2, then 4, then 2. So we're going to have this alternating 4, 2, 4, 2, 4, 2 in the middle. So this point here, this would be having a 4 as its coefficient of a function. This would have 2, this would have 4, and then this would have 1. So the very ends have 1. All of these other middle ones would have 2's, and then the 4's will appear in the gaps. So we have this formula here for Simpson's rule. So let's take a look at an example. We're going to approximate this definite integral from -1 to 1 of the square root of 1 minus x squared dx with n equals 4. So what the shape of this looks like is this function is the top of a circle. Draw this in the middle. So this is going to be the top of a circle from -1 over to 1. So when n is equal to 4, what that's saying is that I need to have my first n equals 0, and then, x sub 0, then I'll have x sub 1, x sub 2, x sub 3, x sub 4. So we've really somewhat divided our region into 4 sections over here. That we had 1 section, 2, 3, 4. So we have the same thing over here. We divide this into these four regions. So this would be -1/2, 0, and 1/2. So using this formula now, I will plug things in with this. So my B in this case is going to be 1. My A is going to be -1. So we start at A, we go up to B. My N we said was 4, and my f of x is the square root of 1 minus x squared. So I put things into the formula. So using Simpson's rule, this area, this is, again, we're just approximating. This formula gives us the area, but this is just an approximation of this. As a note, in all of these, we saw it with this rectangular method, we did Riemann sums. With Riemann sums, with the trapezoid method, and with Simpson's method, when n goes to infinity, when we have more and more of these, this approximation will become an exact. So larger n is, the better this will be. In theory, by the way, in theory. Okay, so this area now, we plug things in. So I'm going to have a 1 plus 1 divided by 3 times 4. And then my function at each of these endpoints, I'll just plug this in. So I'll have the square root of 1 minus -1 squared plus the square root of 1 minus a -1/2 squared plus the square root of 1 minus 0 squared plus the square root of 1 minus 1/2 squared plus the square root of 1 minus 1 squared. But don't forget these coefficients that you have. This becomes a +4. This will become a +2. This will become a +4. So we alternate the 4s and the 2s, and we have the ends of these will always have a coefficient of 1. So when I just plug all this into the calculator and simplify this, I get 1.488. Now, if you know things about circles, you know what the area of a circle is, right? You know the area is going to be pi r squared. Here we have a radius of 1, so the area of a full circle would be pi times 1 squared, or pi. We only have half a circle, that's pi over 2. Pi over 2 is very close to 1.488. Not perfect, but this is at least a pretty good approximation using what we know about the areas of circles. So this is Simpson's rule, Simpson's method. In general, this will usually give us a better approximation than the trapezoid method, but it does just require a few more steps and work.